Our paper introduces an actuator-centered trajectory optimization scheme, and this video presents the optimized motion of our example robots. We begin with the simulation of a soft spring version of the Eptronic Draco. This single-leg robot with a 20-pound load at its hip is driven by two series elastic actuators at the ankle and knee.
We visualize the robot using a stick figure drawn in MATLAB. The large circle on each link represents the position of the center of mass of each link. The black triangle represents the location of the center of mass of the entire configuration, and the small magenta circles indicate spring deflection. We represent the ground contact wrench from the foot using the reaction forces of 2 point contacts. With 4 basis vectors, 2 per contact point, and 4 positive variables, phi1 through phi4, we can parameterize the net reaction force from the foot in a way which guarantees satisfaction of friction cone constraints.
Our linear program creates trajectories at the actuator subsystem level. This figure shows the oscillating deflections of the two springs over the 0.8 second behavior. The initial condition has an equilibrium spring deflection to compensate for gravity. We will now show the jumping trajectory at regular speed. You will see that during the jumping motion we do not simulate floating base dynamics but highlight the motion of the center of mass once the robot lifts up off the ground. Here is the motion. And here it is again in slow motion. Draco follows a jumping trajectory, bending down and springing upward. We can also see the springs oscillating, indicating the storing and releasing of energy. Once the foot releases from the ground, we follow the motion of the center of mass, highlighted in black. We show the jump once more with the ground reaction forces animated. We sum the 2 point contact force vectors at each end of the foot for visualization. Our optimization program is free to change the ground reaction forces abruptly, so long as these forces satisfy the positivity and wrench constraints at each point in time.
We compare the jumping behavior of the compliant robot with its rigid counterpart. For the rigid robot, the spring subsystem is removed, equivalent to being infinitely stiff. Here it is once more in slow motion, and with the ground reaction forces animated.
Through leveraging compliance, the springs are able to store and release energy. As a result, the center of mass's maximum height is 36% higher than that of the rigid robot's center of mass relative to the center of mass starting height.
The paper mentions a zero input falling behavior, a conservation of energy test. Here it is, with the same time step as before. And here it is again in slow motion. The total energy should stay constant. We see that energy fluctuates by 1.8% as compared to the energy gained by the system from falling.
We now show our experimental results from implementing our theory on the torus series elastic actuator testbed. Here is the motion of the system when compliance is modeled. Our optimization method allows for a greater degree of dynamic consistency and a greater final velocity when compliance is modeled, as compared to the optimal motion when compliance is not modeled. Here is the optimal motion when compliance is not considered. This concludes the video portion of our paper. Thanks for watching.